Welcome, everybody. This is a follow-up webinar to the one that we hosted back in November. We covered a number of topics in November, and one of those was around OpenLane design integration options, including kind of power connectivity. We're on this, and in this webinar, we're going to come back and revisit that topic and spend a little more depth and time kind of talking through that and walking through some more of the specifics and showing some examples of different designs and some of the trade-offs and considerations, and making sure that we've kind of provide a little bit more coverage around that topic. In addition, we've also had some requests for to cover our MPW chip bring-up. And Matt's going to cover that as well in this webinar. So those are the kind of two primary topics. We're kind of scheduled for about an hour. We may run a little bit over, but we also hope to have some time for questions, Q&A at the end as well, for any kind of general questions you might have. Okay, so just to get started here. So I mentioned the topics for today. So we'll start with kind of OpenLane design integration options. So as we kind of covered last time, there are really three options. I've kind of relabeled them here a little bit. You'll at the end of this section, I'll point you to a new document that we published that walks through and covers a lot of the specifics of what I'm walking through here. It was built developed by our team, some of the folks on our team. And I'll provide a link to that so you can come back and look at that or refer to that after the webinar. But the first method is what we call a macro first hardening. So this is this first method is a method where you would take your project and you would harden that either into a single macro or multiple macros, and you would incorporate them at the top level, which would be the user project wrapper, but without any top level standard cells. And this is really ideal for kind of more small to medium-sized designs, but one of the advantages of it is significantly reduces the size of the file size and the time and effort to do place and route as well as verification of the design. So that's one that you'll find this example is what was used in the current Caravel user project. We're going to go through that a little bit here in a few minutes. But this is one of the starting point we'd point most people to who are just getting started with using chip ignite and solution and looking at the examples that are provided out there. Second one is we call full wrapper flattening. This is basically where you merge all of your logic, all your digital logic into and you implement that at one level at the top at the user project wrapper, which covers the entire area, right? So it's one of the challenges with this is because you're filling the entire space of the project area. Everything takes more time. File sizes are larger. Sign off takes longer, and your iterations can take time. But it does provide ultimately provides better performance, like fully the ability to fully optimize place and route and provide better performance for designs where you have more challenging constraints or requirements. And the third one is we're calling kind of top level integration. This is one where you have again multiple pre-hardened macros that you're integrating into a top level, but you're integrating at the top level along with standard cells. This method allows for more complex designs. It also allows for you to be able to reuse hardened macros easily, right? So if you can pre-harden macros and kind of reduce the iterations on your complete design time. If you're for your full project, you can also reuse those macros across multiple projects, or use maybe outside or external macros from a vendor, from something that's pre-published. One of the advantages, of course, by placing standard cells at the top level is we can fully optimize timing closure, and so that kind of allows buffering to be placed at the top level and allows the flow to fully optimize timing closure for the design. So let's walk through these in a little bit more specifically. This is a table that I showed last time, kind of talking through some of the pros and cons. I think I've mostly articulated that kind of verbally in the last kind of the previous discussion. So I'm going to move forward to the examples. So the first one is what we call I guess we call it what we call macro first hard. I'm sorry, actually, what do we call it? Oh, macro first hardening, right? So this is the macro first hardening example. This is an example of a user project example, and this is again a case where we're in the blue box, kind of the darker blue box here. You can see this is a sub macro for where the logic is actually implemented. That is pre-hardened and placed inside of the wrapper. In this case, it's placed at kind of the bottom of the wrapper, so where it's likely it's optimizing for connections to the bottom of the user project area. In this case, the bottom pins typically are the Wishbone bus and the logic analyzer pins that go to the management SoC, and then around the other three sides are all the IOs, are the connections to all the IOs as well as some power connections. So in this case, you can see the macro is placed, and then at the top level, it's just basically power. It's just the PDN to distribute and connect power for the rest of the at the top level for the macro to the outer edge of the user project area. All right. When you're hardening your macro, you need to implement some specific options in your config.json file. Again, you can also implement these in Tickle. There's a Tickle equivalence for this in case you're using config.tickle instead. But these are the parameter settings that you'll find for config.json. The document I'll refer to here a little bit later today, or a little later in the session, will also show you the examples of what those configurations look like for if you're using a Tickle script instead for configuration. And we have several examples. I'm going to walk through those here in a little bit to kind of show you some and we'll kind of show you what those look like. But the main options here, you'll find a number of the optimizations. Again, this is the configuration variables for the top level macro, where because we're not placing any standard cells, we need to turn off a number of options related to that piece of it. Okay, so as you'll see, most of these settings are 0 versus they'll be enabled for other scenarios where we're actually placing standard cells in the macro. Okay, so the second one is a fully flattened example. Again, this is in this example you can kind of see the blue here represents likely metal 1, but because metal 1 is in you can find metal 1 in all the standard cells, you're going to see that the entire area is covered with standard cells in this example. And because the logic's been flattened and implemented at the top level, any additional space is filled with either decap or fill cells to kind of consume the entire area, so the entire area gets filled with cells. So obviously there's a lot more detail that needs, your file size gets a lot larger, and then when you're running any kind of verification or timing steps, they're going to take a lot longer to complete as well. These are the configuration settings. So you'll see the synth elaborate only is turned off, and all the other optimization settings are turned on, including power for the standard cells, the power rails for the standard cells, as well as fill insertion and decap insertion. All right, third example here is the one I mentioned, which is where you're basically integrating multiple macros at the top level. This is one example I have here shown with, I believe this is actually our Clear project. We're going to see this here in a little bit, but this is an example where you're going to have multiple macros that you pre-harden. You're going to you basically will place those at the top in your wrapper at the top level, and then you will we'll harden the top level wrapper along with standard cells, including standard cells to optimize all the timing constraints for the full design. And again, you're going to have configuration. These are the configuration settings for the user project wrapper itself. Again, because we're using standard cells, we're enabling all the optimizations and power and as well as the fill and tap and decap insertion. All right, so let's so before I talk about before we go and look at some examples, I want to talk a little bit about power connectivity and routing as well. Basically, for the three options we described, the second one, which is where we flatten the entire top wrapper, pretty much powers routing is handled automatically because that's done as part of PNR. Everything's flattened, so you don't have to worry about connectivity to any sub macros in that scenario. For the other two options, though, whether you have standard cells at the top level or not, but you have sub macros placed at the top level, you need to be concerned to make sure that those macros are powered correctly. And there's really two approaches you can take. One is a hierarchical method, which is leveraging kind of PDNs, a grid array or PDN or a PDN array or grid, and the other one is a ring method. So we're going to walk through each of those more specifically. All right, so for the Verilog, for either of these two methods, it's important to ensure that for connectivity to be made, there's a couple of steps you need to ensure is implemented correctly in your design. One of those in your Verilog is that you need to include the power pins both when you instantiate the macro as well as within the definition of the macro itself. Again, we're going to look at some examples of that coming up. And then in the config.json, you want to make sure that you've enabled a couple of key variables to connect, to make sure that power gets connected. So here, there's one called FPN macro hooks, where you're identifying for your sub macro what are the power connections that need to be made, and then there's a use power pins define, which enables these power pins to be utilized for part of the PNR flow, as well as you want to turn off this PDN check node since it does not typically work well in hierarchical mode. So this is so these three settings are important in your config.json. This is the example of kind of the tickle implementation of that if you're using config.tickle for OpenLane. Again, we'll take a look at some examples of that here shortly. So in the hierarchical method, in terms of power connectivity, you're connecting power through a grid of rails that basically at each level of your design. So from your top level to your kind of first level macros to kind of macros that are contained inside of that. One of the considerations is that as you go down in hierarchy in each layer, you lose one layer of metal for routing power, right? So in your top level, the primary way to connect power to your macros is going to be using metal 5, and those are going to be intersecting with metal 4 straps in the next metal macro down. So in this case, in macro A, you can see these the verticals here. The horizontal straps are metal 5 in the top level, right? They're routing power. In macro A, which is the first level sub macro, the primary connections are done through metal 4 vertical straps, and those are connecting to the horizontal straps in the top level through vias where they intersect and cross, which you can see through these like green dots, right? And then in the next level down, in the sub macro, you're going to be doing something similar. This doesn't quite look the way I expected. But you're going to be connecting the macros, the sub macro B here. The power connections are made through the horizontal straps that are shown on metal. These would be on metal 3 in this case, kind of in this section here. If you can see these lower ones here, and those are being connected to metal 4 in the macro A. Kind of through these vias placed, where they intersect here. right? So that's kind of how power then is connected and propagated down through the design. Obviously, as you go further down the design, you lose more routing layers, and the complexity of your sub macro is more constrained as you do that. All right, so just a couple of the other considerations. Obviously, when you're placing macros, you need to be concerned about the orientation of the macro. So, you need to make sure that your straps are matching at each level. So, for example, macro A has its power straps are on the metal 4, which are vertical. If I rotate it 90 degrees, they won't be able to intersect the metal 5 straps. So I have to have to keep it not rotated or rotated a full 180, or kind of my options. Same for the sub macros. With going down, they have to be kind of again oriented with consideration of the next level up that they're integrated into, so they mate correctly. The other thing to consider is to make sure the macros are large enough to intersect the straps at the next level up. So in larger designs, you may have a macro that's very small, and the pitch between your straps may be larger than the actual size of the macro. So you need to think about placement of the macro, or the overall size of the macro, or the pitch of your straps, to ensure that you have sufficient power connectivity to the sub macros. There is a possibility. So if you look at the very top level user project wrapper, it routes all the power domains available, which in some cases you may run into a situation where you don't need all those power domains and you would like to get more density of the power straps. That does require customization. You can look up and find some additional documentation examples of how to do that, but that is definitely more complex step, or more advanced step if you choose to try to go down that path. Also, you'll notice, like in these designs, there's some metal stubs hanging off at the ends. Those are generally not an issue or a concern, but they do affect kind of power density or routing, and so there is an option to try to trim those stubs that you can set in OpenLane to try to minimize those stubs in your design. Okay, I think I got it. All that one. So the second one is the ring method. So in the ring method, you're implementing a power ring around for each sub macro that goes around the perimeter of the macro, and then power is connected to that. So the advantages of this is that you have all the kind of within the core area of the macro, which is inside of those power rings, you have the full set of metal layers to route with, and so it allows you to have very complex, more complex macros. The downside is the rings take additional space, and so they can be less efficient depending on your design to implement rings. But basically, in this case, every sub macro is implemented with rings, and then they're connected to the periphery, like you see kind of in the diagram here. Okay, so this is just an example of power configuration settings that are important. The left is for straps. This is kind of by default what OpenLane is already set up to do and will do by default, so you generally don't have to worry about changing or adjusting any configuration settings. For rings, you do need for the actual sub macros themselves, you do need to modify the some PDN parameters shown here on the right. Again, more specifics of this is in the document that I'll reference. But one of the main ones, of course, is this first parameter here, where you have FPPN core ring is set to 1, which enables the implementation of the ring power ring for the macro. And then you have a number of other settings here related to the width of the routes for the in the ring, how wide each of the straps are, or the routes are, kind of the offset between the offset of the ring relative to the edge of the macro, and then kind of spacing between the rings, between the power routes in the rings. Okay, so let's take a look at some examples. I'm going to go out of, oops, you go out of full screen mode, and I'm going to show you some examples here. So these, I've opened up a number of examples in KLayout just so we can take a look. So this is the user project wrapper. Again, you can kind of see if I were to zoom in here. So I'm looking at the whole thing. This is the full wrapper. The top part of here is just all power routing. This, the actual sub macro is implemented down in here. So if I were to open this up and turn it off, you can kind of see how it's placed. Right. Oops. If I zoom in, you can kind of see the blue or purple here. Vertical is metal 4, and the horizontal is metal 5. You can kind of see where they're intersecting, and vias are placed to make connections between the sub macro and the sub macro and the top level power routing at metal 5. Okay. So let me go ahead and move on to another example. A couple more examples similar to this. So this is, again, another one with a sub macro. This is an AES accelerator implemented kind of in the lower left corner here. Again, I'll zoom in a little bit so you can get an idea what that looks like. Again, this is implemented the same way, where you can kind of see metal 4 and metal 5 intersecting and to provide connectivity to the sub macro. If I were to go here and turn off the block, you can kind of see this is the power routing for at the top level, right? And you can see the metal 5 straps running across the top of the macro, and then they're intersecting with metal 4 straps in the macro via via placements. All right. Let me switch over and show you a more complex example. So this is the this is the last third example I showed, where you have multiple macros implemented at the top level. This project is called Clear. It's an open source project that you can find, there's a reference to that, I think, in the documentation. But again, here we can find, if I were to look in here, there's multiple elements of this macro. So let me see. So in this particular case, we have one large sub macro at the first level, which is the FPGA core. So if I turn that off, you can kind of see that how that's placed, right? And you can see metal 5 straps going across that. So here, this was implemented without a ring, right? And it's just intersecting through metal 4 straps in the FPGA core. I turn that back on. Now, if we look at just this macro itself, it contains multiple sub macros. So if I turn off, some piece of that, you can see the bottom corner here. This is one of the sub macros that was placed inside of the next level, called bottom left tile. And I don't know if that one's implemented with a ring or not. Let's see. Doesn't look like it. No, this looks like this is also using straps as well. So it looks like this example I'm not sure if Mohammed Shalana, if you're familiar with, is there any of the sub macros you're implemented with rings? Are you aware?
So the macros aren't implemented with rings.
They are.
They have like vertical metal 4 stripes, and those are connected on metal 5 and the next level.
Okay. So if I were to look at is there an example of one of these macros that you'd recommend? Or is any of them, are they all the same?
They're all the same, more or less. You can pick like a tile.
So this is an example of the, I'm going to turn off some of the lower layers and just look at the routing power. So this looks like, I just see metal 4. Let me see metal 5. So I see metal 4 straps. I don't, like this example, I don't quite see the ring.
So there are no rings in the tile macros. There are only metal 4 stripes here, and those are connected using metal
Oh.
5 on the upper level.
Okay, so that's what you're saying. There are not rings implemented.
Yeah.
Okay. All right. Sorry, I misunderstood. Okay, so let me switch over to another example. Are there rings implemented in the OpenFrame project? Are you aware? I think there are rings definitely on the. So we can take a look at So in the center of this project is an SRAM, and the SRAM has rings implemented. So if I were to look at, if I go find the SRAM itself, this larger macro inside here is a Pico. It's an SoC based on Pico RV32 that Tim had designed. Oops, waiting for it to come back. All right, let me go ahead and show you what I wanted. Inside of that, there's some memory macros. If we take a look at one of those, okay, you can kind of see here the rings on the outside, right? So these are the power rings I'm just referring to. So this is probably just power and ground. So one of each. That's supplying this macro. And then now connectivity of this macro, if I were to go back and look at the next level up where this is used, you'll see how those mate. Looks like it's at this level. And if we turn off all the other metal layers, let me leave metal 3 back on. So now we can see need some vias. Oh, I'm missing via 4. Yeah, so here we can see these metal 5 straps running across the top of the SRAM macro. Right here, if I turn off the SRAM macro real quickly, you'll have a better sense of that. So there's the SRAM macro there, and you can see the power ring. I'm looking at the upper left corner of the power rings, and you can see the vias mating to the metal 4 vertical straps as part of the ring. Okay, so hopefully it gives you a little bit of sense. We'll try to maybe we can do some follow-up with some other examples as well that you can take a look at. So I'm just conscious of time. It's 9:30. I want to leave some time for Matt because he's got a lot of good content around Bringup. Let me see if I missed anything else on my topic. So this is a link to the document I mentioned, where you can provide some more detail of what I just walked through. Sorry. Yeah, that's correct. That was that there. And then again, I think one thing I was hoping to show you as well, just to ensure you understood, is the implementation of power pins, right? So this is the Caravel user project example. I'm in the RTL, looking at the RTL for the user project example. So if I take a look at the user project wrapper, this is the top level wrapper, and inside of here we instantiate a one sub macro, and it's called mproj or mprj. You'll see the use power pins defined at the very top of that macro where we instantiate it, right? And then in the next the modules implemented inside of this file called user project example.v, and in the module definition, you'll see at the very top of the definition the use power pins guarded by, the power pins guarded by the use power pins defined. So it's important that you have both of those included. Also, it's important that you have the the macro hooks included as well. You can actually go all the way through a PNR, and the design will look like it passed successfully, but you don't have power connectivity connected. And the only way to know that is to be able to, well, even with a full LBS, you won't catch it if you don't have power connected correctly in your Verilog, right? So you can, if you don't have power connected in your Verilog and you don't have an FPN hooks, you'll just basically you'll get a design that looks like the cell's been placed and implemented, but the power connectivity hasn't been made to power that macro. So something to be aware of and check in your designs to make sure that your power is indeed made to each of your macros. Okay, I'm going to stop there. Any other ads or things I missed? Anybody on the team here that I didn't cover that I should have, or anything I need to correct that I said?
Well, from the questions and answers, some people have been wanting to have the links to the various places that the repositories and other locations posted in the chat.
Oh, in the chat? Sure, absolutely. So let me do this. I'll share this file link in the chat for the Zoom. This needs to go to everybody. All right, so here's the link to the document that I mentioned. And this document has a lot of the details of what I described. And in here, you'll find also links to each of the design examples that I was showing. Okay. All right, well, if there's no other questions for now, I'm going to turn things over to Matt, and he's going to walk through some of the chip Bringup topic.
Bringing up your chips. And there's still a couple of open questions in the Q&A panel. So Jeff, if you want to take a look at them, maybe you can do like text replies.
Great.
And Matt, can I launch the questions?
Yes, please launch away. So yeah, if you can fill in this little form for us, we appreciate it. And in fact, if you don't fill it in, then I won't show you any chip demos. So get clicking. So yeah, what I asked in the Slack. So if you're not a member of the Slack, then you should consider joining. That's where a lot of the discussion happens. And I asked, what else would people be interested in for this webinar? And one of the questions that came up that there was quite a lot of enthusiasm to know more about is how to interact with Caravel, how to write firmware, how to use the Wishbone Logic Analyser, GPIOs, and so on. So I've put together a little demo that I'm going to run now. I will just, I'll share my screen now. So I've put this together so far in my fork of Caravel board, which is where all the board files are and where all the firmware is. So I'll drop that into the chat. Just got to remember I type it into everybody, to everyone. And I'm hoping to make a pull request soon, so that will become part of the eFabless Caravel board. But for the time being, it's just in my branch. And you can follow along with these demos and check the firmware here. So we're going to start off by looking at, and then I've got some documentation up here. So this is where the main Caravel harness documentation is. So this is the area here where you put your design. And then we've got for the chips, so you're getting back on MPW 6 and 7, down in this bottom part, the management core wrapper, that is using this, which is a Litex core using VexRisk. And this is where the SPI, the DLL, the GPIO, the UART, the logic analyzer, the stuff that I'm going to be going through today is all based. So that's the source of the documentation. The source for the board files is here, and there's instructions on GCC, because that was one of the questions that kept coming up in the Slack, was how to get the compiler going. And we're going to start off by looking at the HKDebug demos. So part of Caravel is the housekeeping SPI, HKSPI, and we can talk to the chip using that, and that can save some time. So if I come over here, I've got a make file in there, and when I run HKDebug, it just runs this script that's in the repository called Caravel HKDebug. It fetches some information out of the chip, and then I can do something like read the project ID, and it tells me what the project is. So it was on the 2206 shuttle, and then this is the ID because it's one of my chips. We can also reboot Caravel, which can be useful sometimes. So we can do that by typing 3, which is here. And we can also enable and disable the DLL. So that's being able to change the internal frequency. And that's pretty useful being able to do that remotely, because it can save a lot of time if you're messing around in firmware, trying to get that to work. So at the moment, I've got the board running. You can see the frequency of the LEDs are flashing here, and the little GPIO LED is flashing there as well. And if we take a look at the firmware that's running at the moment, I've just got this GPIO demo defined. So all it's doing is forever blinking, and blink is just setting all the IOs off and then setting them all on with this little delay in between. So let's see if we can change this frequency on the scope over here by engaging the DLL. And we can also read all the registers and see what they're in. And the important ones for us are register 8, 9, 11, and 12. And they relate to the PLL, the DLL registers. I like this calculator, which was made by Konrad Beckman. So that's quite a nice way of generating lists of the registers that you need. So I've already got that installed, and I can get a list of all my available. So let me just quit this and show you that. So I can also run a list. Just move this out of the way. So I can, instead of telling it what clock out frequency I want, I can get a list of everything that's possible. And then if I say want to increase it up to 30 megahertz, because our input clock is 10, then I can say, instead of listing generate with the output 30, and then it's telling me, okay, I need register 11 is O1B and 12 is OX09. So let's set that. So using number 14 to set the register value. So I've already forgotten. OX11 is OX1B. OX11, OX1B. And then I can read all the registers, and I can see that that is changed. And then I needed to set register OX12 to OX09. Oops, I messed that up. OX12, OX09. So we've got them there. And then I can enable the DLL by using option 8. If I just drag the scope in, thank goodness it worked. Bit of a dangerous live demo there, but now we can't see the LED. Well, you can kind of see it flickering a bit. It's going a bit too fast. And now on the screen, we've got a faster, the rate there. And if I turn it off with option 10, it goes back to where it was before. So that's really useful for playing around with the DLL from the command line. Let's see what else we've got. There's also the DCO mode, which is enabling a different type of internal oscillator. You can set any register value that you want, and reading them all out is pretty useful. I've already shown you those. So let's move on now to the firmware demos. So one of the other things that has been confusing people on the Slack is when they run make they get a problem. So often it might look like this, their problem. If I do a make clean and a make, they'll get an error. And especially people who are new to Linux, they're not used to understanding how to read errors, which I understand it can be a bit daunting to start with. Normally, it's good to work your way up from the bottom. So here I'm seeing command not found because it doesn't know where my GCC is. So if you've installed your GCC, RISC-V GCC somewhere else, you'll need to tell it where it is. So that I do that here. The default is this one. The other way of doing it is setting an environment variable. So you can override this by exporting an environment variable, and you can do that like that. And once that is correct, comment that out again. I can do a make. Now I get no error. And I also have this demos.hex. And that's the file that we're going to flash. And then I do a make flash. Make fla. So if everything's working well, you'll see the Caravel data coming in here. It resets the chip. And as that's happening, we can see that the scope is not showing anything. And now it's started up. We've got the LED flashing again, and we've got the waveforms on the scope. One of the other problems that people have is they can make the flash, but then they can make the firmware, but they can't flash it. So check the board is connected properly. Check that the FTDI device is there. So that there's a command to do that called LSFTDI, which will show you any FT devices found. So it definitely has got to be there and plugged in. Maybe your USB cable's a bit shonky. Check you have permissions. That's a real classic. So I think this is on TTY USB 0, and it's in group plug dev. And I'm also in group plug dev. In other distros, it might be in group dial out, and you need to be in the same group. So if that's biting you, then check out these instructions. Check the M2 breakout board is properly seated. I found it doesn't need to be screwed in. But it's worth checking. And if you get stuck, then make sure to ask on the MPW 6 Plus Silicon channel. I think that's probably the best place.
Matt, one other common issue too is one other typical issue I've seen is people configured or reconfigured those the IOs for the housekeeping SPI. So
yeah.
If we have time, I can cover a little bit of that too, where we can talk about that.
Yeah. Yeah. So which was that on MPW 6?
Well, actually, even on any of them today, right? So if you look at the right there you go. So if you look at these first 5 IO are kind of critical. So the first one's related to debug. There's a debugger UART that has a Wishbone master, and if it's enabled, there's a concern that you can screw up the Wishbone communication. So typically, we want that to be either disabled or tied low to prevent it from like toggling or enabling the debug mode. So that's 0, and 0 is typically, I haven't seen too many people having problems with 0, but the next 4, 1, 2, 3, 4. Those are the IOs that overlap with the housekeeping SPI interface. That's the same interface we're using to flash the firmware. So the Caravel wakes up by design, though you cannot like change the default power on state for those, but you can change them at runtime with your firmware. So your firmware can change those configurations from their standard defaults to something else. And if you do, as soon as the firmware runs and reconfigures those IOs, after a power on resets, you will not be able to talk to the housekeeping SPI, and you will therefore not be able to flash. So the way around that typically is you want to power up your board while keeping the processor in reset. So the way I do that is I hold down the reset button, I plug in the board, I keep it held, and then I start the flash. And as soon as the flash starts, you can typically release the button as soon as you start to see it talking or starting to flash. But you can also hold down the entire time and it'll complete successfully. Hopefully that helps.
Thanks, Jeff. Yep. Okay. So we've just seen that flash happening. And just to continue on a little bit from what Jeff was saying, in this configure IO section is where we set all the pins up. And there's some useful defaults here. Management means it's controlled by the RISC-V processor that we're programming right at the moment. And user means it's your design that's instantiated inside Caravel that is going to be connected to the IOs. So for these demos, everything is controlled by the RISC-V core at the moment. And then we have to start this transfer and wait until it's finished for that to work. So typically in your main loop, you'll run this configure IO and that will do that. And then when the program continues to run, then everything will be set up correctly. So we've just been running this demo so far, GPIO demo, which is just blinking. And the next thing I want to show you is, just a little bit more info. So because there's 37 IOs, there needs to be two 32-bit registers to control them. So reg mproj data L, data low, is the first 32, and then data high is the next 5. So it's only the least 5 significant bits of data high that do anything. And to read from them, you just read directly from those registers. So the next thing we're going to do is set the DLL in firmware. So we say we've done our experiment, we found out a good new frequency we want to use, and now we're going to do that in firmware. So I can come up here and turn on the DLL demo. And then what that's basically doing is setting those two registers that we used before, and then enabling the DLL, and then switching over from the external 10 megahertz oscillator into the 10 megahertz, into the now new 30 megahertz oscillator coming out from the DLL. And then this line puts the Wishbone clock and the user clock, I saw that question answered by Tim a little while ago in the Q&A, out on pins 14 and 15, which I have here on the scope. So when this happens, these will no longer be coming from the RISC-V processor toggling the bits, they'll be coming directly from the clock. So let's see if that works. So I'll write that and then make flash. And then we get a lot faster frequency there. Let's see if I can just read it from my scope. I think I probably need to zoom in. Deep zoom. So that's reading 29.5 megahertz measured by the scope, which is what we programmed in. And we've got both clocks the same. You can have the Wishbone clock different to the user clock if you want. And then I can turn that off by just commenting this out and then flashing that again. So the next thing I want to show you is serial communication, because that's really useful to do debugging and talk with your design. Caravel's got a serial UART on pins 5 and 6, but because of the way the FTDI chip is used to flash the firmware, it's not easy to at the same time use it to read and write on the serial. So there's a jumper on the board called J2, it's in the top right hand corner of the board. And that needs to be set for us to be able to talk to the serial through the FTDI. So first, to try this demo, you've got to first enable the serial demo. So let's take a look at what's happening there. So it enables the UART, prints a little message, and then we just run this little loop here that is waiting for a character, and then it's going to be able to print something, print some hex, it's coming from an internal register and blink the LEDs. And then I will flash that. Okay, I've just noticed that I need to reset Caravel. So if you do see something like this, it's worth pressing the reset button. I think that's because of when I change from the PLL to the non-PLL, I need to reset the housekeeping SPI or something like that. Okay, and then the next thing I've got to do is to place that jumper. And then I have a make monitor. Oh, look, I'm getting nulls here. It's probably because the PLL is still active. It wouldn't be a live demo if something didn't. Oh, look at this, and that HKDebug isn't working. Let me try another reset. It was working earlier, so let us know if you try it and it works, or if you try it and it doesn't work, and I'll try to figure it out. And the last thing I wanted to show was the Wishbone and the Logic Analyser. And unfortunately, it's not really possible to make a demo for everybody because it depends on what's actually enabled inside the chip. So I'm using this chip that we submitted to MPW 6, and we have an SRAM with a block that connects it to the Wishbone. So I can read and write via Wishbone to the SRAM block. So I can show you at least what the, oh no, I don't want that. Oh, I know what it is. It's because the GPIO demo was also enabled. So it never gets, it just comes here and then never moves on. Dang. All right, well, that's flashing. I'll just explain what's going on with the Wishbone demo. So this also uses the logic analyzer because it's got to enable the way that Wishbone multiplexer works. So it enables the output. So they are a bit confusing, the registers. OENB needs to be set low to enable the output. Input enable needs to be set low to enable the input. You write to this register and you read from that register. So here we're enabling the inputs, we're enabling the outputs, and then we're writing some data. Then I enable the Wishbone bus, that's really crucial, and turn on the UART because I'm going to print some data. And then writing to RAM, that is done using this macro, and that macro is just basically defining a volatile, that's important, and then writing data directly into memory at this address, which is specific to my project. So let's just check to see if the serial demo works now. Yay, okay, so A for hello, B for printing out the count, and C for flashing. So hopefully you see the scope responding and the LED blinking. Oh yeah, getting some love from the emoticons, give it up. All right, so let me now enable that Wishbone demo. And what this is going to do for my project is just going to write into the RAM, and then it's going to read out from RAM. So what we should see is just hex 0 to 15 being printed out from those first 15 registers. Yeah, uncomment this, flash the firmware, place J2, start the serial monitor, and then reset Caravel. Okay, so put on J2, start the serial monitor, and then reset Caravel. All right.
There you go.
There we go. And hopefully you see there's no magic here, nothing up my sleeves. We're just writing to this area in memory that's above OX3, and then we're able to read back later, and that's all happening via the Wishbone and with the Logic Analyzer. So hope that's helpful, and if you get stuck anywhere, then just reach out to us on the Slack. MPW6 Plus or Caravel or Chip Ignite channels are probably the best ones to go for that kind of stuff. And that's it from me. Thanks.
Great. Thanks, Matt. So just want to do a couple minutes on just some questions we have. Mohammed Shalani, you still online? There was a question around OpenLane and M1 Max. I don't know if you what the latest is. I know we've been working on that, but is that still in progress or?
Yes, in progress. It's the ARM, like the Apple Silicon, is fully supported by OpenLane 2. For OpenLane 1, basically this is work in progress.
Okay, so that might be something to look at as OpenLane 2. There was a question on going back and looking at the pros and cons. I can do that here in a minute. What are the norms, standards you recommend while chips architecture lifecycle management process? Okay, so that's a pretty big question around just development process and lifecycle. We are working on trying to provide some more guidance on that in the future. So that's something that I would kind of be on the lookout for coming up. But we don't probably have. That's probably a bigger topic than to cover right now. What are the chips? Let's see. MPW6 can apply HV process material to integrate. Is there access to the last project used for the Logic Analyzer tutorial so we can look at how everything is set up? Matt, are you going to be able to share that project, or is that shareable?
Yeah, I'm going to make a pull request. I made a new demos directory alongside Blink in the Chip Ignite firmware directory. So I'll make a pull request, and once it's merged, it will be in the normal place. But for right now, I can just drop the link again in the chat.
Okay. All right, there was a question around pros and cons. Just again, let me just show that real quickly. So on the pros and cons slide that I had here, let me move that. This is the pros and cons slide I believe you're referring to. So I think I covered a lot of this in the conversation, kind of what I described in the previous slide. But basically, for the macro first hardening, the pros are that it's fairly simple. It's simpler to implement. It's the example that we provide, kind of as if you were to clone Caravel user project. One of the biggest things is it doesn't require a lot of compute time and resources because you can constrain the size of your macro based on the size of your design, right? And then the rest of the integrating at the top level, if there's no standard cells, is very lightweight and very fast to do. The challenge is that it can be complex and difficult to meet challenge or tight timing constraints because you have a macro that's placed at the top level and you have wires connecting from that macro out to the periphery of the user project wrapper, and there's no ability to close or to improve the timing or optimize the timing along those signals. The best you can do is try to place the macro as close to the critical signals as possible. But if you have some other, IOs or signals that are far away, you're not going to allow OpenLane to be able to optimize those paths in your design. And so it can be challenging to meet something that has tight timing constraints. On the full flattened one, again, it does allow for complexity and kind of fully optimized designs. The challenge is that your design gets really big really fast because you basically are filling the entire area with cells, and that will generate much larger files and will take much longer run times. And so that's one, and also it also limits any reuse. So anytime you may have any small change at all, you pretty much have to do the entire flow again, which is and you can't take some piece of it you've done and reuse it in another design easily. You just take the raw Verilog and you have to basically re-synthesize everything. In the top level, the third option allows for a lot of significant level complexity, allows for like mixed signal designs, as well as pure digital designs. But one of the big things is allows you to kind of decompose your design into blocks. You can pre-harden those blocks, and when you iterate, you don't have to like reharden the entire design. You just reharden the block that was affected, as well as any level of integration above that if you've changed any of the external connectivity to that block. But the pros is that you can fully optimize the design in terms of you're allowing kind of the OpenLane to fully optimize the design from a timing constraints perspective, because it can place standard cells at the top level, and it can manage the timing for those paths within the design. So hopefully that provides a little more context. Again, feel free to send more questions via Slack. We'll try to respond to those, as well as look at the document we sent. There's another document that just talks about timing closure as well. I'll try to remember to include a link to that as well, if you have more questions around timing closure. Okay, I'm going to stop with that. Any other questions that we didn't cover that we should hit? There's a question around, and Tim, you may be familiar with this. MPW6 can apply on a HV process material, high voltage process to integrate. Oh, 750 volts. No, I don't think so. Right? We don't have any.
Not on Skywater, no.
Not on Skywater, no. Okay. So that's a no on that one. And then just a question around whether or not there is another free MPW shuttle. There is not currently anything planned like the Open MPW shuttles. There's nothing currently on the calendar right now. There's continued work within the industry to look for that we're trying to identify and acquire find more sponsorship for shuttles like we've been doing in the past. And so I would just continue to stay tuned. There are some other specific opportunities, like if that may be related to contests or requests for IP that you may also see coming out in the future, where you'll have opportunity to get fabrication sponsored through either eFabless or through another party.
And don't forget Chip, Ignite, and Tiny Tape Out if you want to pay to get guaranteed silicon made. Absolutely.
And the slides will be sent out. We're going to send those out in a follow-on email to everyone who registered, as well as we will post the video on YouTube and provide a link to that. Okay. I think we covered most of the key questions. So
yeah, I think that's a wrap.
Yeah, I think so. Appreciate everybody attending, and look forward to seeing your designs.
Yeah, thanks everyone for coming. Have a great rest of your week and a good weekend.